All right, here's our video. Painted Black. A little shout out to the Stones, their number one hit of 1966. Actually, that's Raga Rock hit, which is Indian influence. Brian Jones was on the sitar for that album. And it's fitting for this video as we talk about Black Dwarfs because Painted Black is about death. This guy is grieving over the death of his wife or his girlfriend or whoever. And Black Dwarfs are about death. The death of a star. And we're talking about the death of a white star, a white dwarf star. But here it is. Wait for it. Black dwarfs do not exist. But listen, they can exist. So let's get our pen ready. Very important. They don't exist now, but they can exist. So look right over here. They can exist. But they don't. They don't right now. In fact, we should actually say they will exist in the future. They will exist in the far off future. That's the thing about black dwarfs. So if we think about the here and now, let's put the here and now right over here. The here and now. My here and now. Or your here and now. You know, you're watching this video at a later time. And it really doesn't matter when you're watching this video and listening to this video. You could be listening to it in 1,000 years. It would still be insignificant. You could have listened to it in 1966. If, it wouldn't still matter, right? Because way out, there's our line, way out in the far future, where we see a black dwarf being formed. We're talking, right over here, we're talking trillions of years, if not quadrillion of years, way out in the future. And we should know that the universe, our universe, is only about, put this little about sign over here, 13.7 billion years old. So as you can see, the universe is too young for a black dwarf. And if we see a black dwarf, then that will change our whole perspective of the age of the universe. So in this video, we'll use our sun, and we'll look at the stages of our sun's life. And I will explain how our sun will eventually become a black dwarf. Again, trillions of years into the future. So let's get a clean page. So here's our sun. Our sun is let's get our pen ready first. Let's use blue. So our sun is a type G star. We'll put it over here, type G. And it's about 4.5 billion years old. So it's a type G star. It's a yellow dwarf. Right? It's not as common as red dwarfs, like Proxima Centauri, which is our closest star besides our sun. It's about 4 light years away, around that. But it's bigger than a red dwarf, not as common. And it has, our sun, since it's 4.5 billion years old, give or take, will eventually turn in 5 billion years, and some scientists debate this, maybe some say 6 billion, 7 billion, but roughly, let's put this roughly, 5 billion years, the sun will become a red giant. So that's the first stage, and let's talk about that. All right, so here we see the life cycle. And obviously you can see where we are now. Let's go back to yellow. So again, our sun is a yellow star. Here it is. And what's happening now is the sun is burning hydrogen. So it's taking hydrogen, the lightest element, most abundant in the universe, and it's going through nuclear fusion. And so hydrogen is being fused into helium. So hydrogen is an H and helium is He. So we're taking 4 hydrogen and it's being fused into helium. And that's happening in the core of the sun right now. But in the far off future, we said before, in roughly 5 billion years. So we have some time. If you had something planned in 5 billion years, you should actually cancel, right? Because when our hydrogen in our sun runs out in the core, remember it's important, in the core, what will happen is it will expand. And this little dot may be Earth. So there's little debates on whether it will expand beyond Earth or just to the edge of Earth. Either case, we wouldn't be able to live on Earth. So what will happen is the helium, the core of the sun will just become helium. And the pressure will be enormous inside the core. And what will happen is the outer layer will expand. So we're looking at going to the orbit of Earth. Big expansion. So again, basically, very simply, the hydrogen in the core will run out and there's only helium left. And the outer edges of the outer layers of the sun will expand. The hydrogen will expand and cool and turn red. That's the second phase. Again, the 4 hydrogen atoms are being fused into helium. And that core will cause enormous heat and enormous eternal pressure. Let me get a clean page here. And I'm going to go back to yellow. Got the yellow pen going. Use that yellow. So again, if we make this the core, now the core will be, put a little arrow, helium. And so the gravity will be intense. The heat is going to go very intense. And the outer layers are pushing out. And remember, the hydrogen is cooling off and turning red. But then, when you get this helium core, you can get degrees of about 100 billion degrees. Imagine 100 billion degrees. And now the helium is going to fuse. 3 helium atoms will fuse into a carbon atom. That'll be the next phase. And when that happens, again, the enormous pressure coming into the core will also cause a reverse pressure going out. So you'll see the second expansion. And let me show you that picture. And right over here, we got make sure the pen's ready though. There we go. And here again, there's the arrow. There's the second expansion where it becomes a red supergiant. Now it has a carbon core. And as that's going through this process, remember, this whole process will last about 1 billion years, when finally the core will not fuse anymore. It will run out of fuel. The sun is not big enough. It is not massive enough to go even further, because if it had more mass, it can fuse heavier elements. But the sun will never fuse carbon into iron. So at that point, the pressure gets immense. And you can see the next phase, this planetary nebula. Because of the core itself, this carbon core, the extreme pressure and the stoppage of fusion, the outer layer will expel, and it turns into this planetary nebula there. So again, just remember that fusion stops and gravity is taking over. So all this enormous pressure is coming inward, where all the outer layer is going outward, like a pressure cooker. And you'll be left with this white dwarf. Little white dwarf. And again, if the sun was massive enough, that white dwarf could become a neutron star. And if it was even more massive, it could become a black hole. But our sun is only a type G, yellow dwarf, so it'll never become a neutron star or a black hole. And I have other videos on how that happens. But right now, for our sun, it will become a white dwarf. All right, and here's our white dwarf. You can see it's almost the same size of Earth, but it is extremely hot and extremely dense. It's hotter than the sun. It can reach temperatures of about 180,000 degrees Fahrenheit. I'll write that down. So it could reach temperatures of 100,000 Kelvin. We'll just say about 180,000 degrees Fahrenheit. Much more massive than the sun. Much more massive than the sun. And cooler. And hotter, I mean. The sun is cooler. Much more massive. Not in, I should say, much more mass. It has much more mass, not massive. It has much more mass than the sun. And hotter, but much, much smaller. Add another much there. So let's add 3 muches. And you can see the size of it. So it's not going to be as bright as the sun, but it'll be more dense than the sun. Now, the thing is here, it doesn't have nuclear fuel. There's no fusion going on. It's only gravity, the pressure of gravity causing this to be hot. But over time, it'll fade away. And that's when a black dwarf will finally come about in 1 trillion years. So if we look at the whole process again, we'll put it over here. We'll use red, change the color a little bit. So from the star itself, from its star itself to a red giant, this big red giant over here, that will take about 5 trillion years. 5 billion years, not 5 trillion. And that will last about 1 billion years. Billion, not trillion. And then it becomes a red supergiant, and then it will expel its outer core, becoming a planetary nebula in a very short time. In a very short time. The planetary nebula will probably last only 75,000 years. Very, very short time. And then it becomes this white dwarf. And that white dwarf could last trillions of years. Trillions or quadrillion years. That's why we do not see black dwarfs in our universe today. So if we go back to our black dwarf, what it may look like, they're not technically dead either. Well, you might say a white dwarf is dead because it has no nuclear fusion going on, but it's still, in a way, hot. And a black dwarf may be hot too, because it's not emitting any visible light. So let me write that down. It won't emit no visible light. But remember, visible light is only a small part of the spectrum, because it will still emit, not admit, some other radiation, light radiation, infrared specifically. And so we're talking about a temperature range that it still could have anywhere from 600 Kelvin, which is about, I'm using in Fahrenheit, it's about 620 degrees Fahrenheit. Still hot, right? Not like a sun, though, if you put it in perspective. But it can also go down to 5 Kelvin, which is about negative 450 degrees. That's close to absolute zero. 0 Kelvin is absolute zero. So black dwarfs could still be hot, or they can be cold. They can be colder than Pluto. Now, what would happen after that? This is all conjecture now. We're not sure, because black dwarfs, again, they have this carbon core. They may just be a piece of carbon. We know that carbon could become a diamond, maybe. So this is where there's a lot of debates on what a black dwarf will actually be. Will it be solid like a diamond? Will it be gaseous? But eventually, though, it could lead to proton decay. And this is debatable because we're not sure protons do decay. We've never observed the proton decaying. So a black dwarf may go through proton decay, which is hypothetical. And then after that, it may just evaporate into an exotic form. We'll put a little arrow down here of hydrogen, liquid, metallic hydrogen, I should say. Metallic hydrogen. We're not actually sure about this. So again, just to review upon black dwarfs, our sun, which is right now a yellow dwarf, in about 5 billion years from now will become a red giant. And that red giant will expand again. It'll last for about 1 billion years. Remember that the sun right now is fusing. It's a nuclear reactor. It's fusing 4 hydrogen into 1 helium. And eventually that helium on the outer layer will expand when it becomes a red giant. And then it'll be fusing helium into carbon. And when that happens, it'll be a next second kind of an expansion and a third expansion, where eventually it will expel all its outer layer, become a planetary nebula for about 75,000 years, a very short time. And then what would be left is just this white dwarf, which has enormous amount of mass, enormous amount of temperature. And over time, that gravity and pressure, as a white dwarf, remember, it's not going through nuclear fusion, it will eventually just cool down into a black dwarf. And from that, proton decay and hydrogen. By the way, when our sun does become a red giant, you can see the habitable zone, the Goldilocks zone, will be Jupiter and Saturn. They'll be in the Goldilocks zone. And the radiation from the sun, from that red giant, may evaporate these planets over time. There's some debate on that. And the only, if we're thinking about the moon of Saturn, Titan may be very habitable to life. And that's another video. So again, going back to our black dwarf. Remember, our sun won't become a black hole. It'll become a black dwarf. And the gravity on a black dwarf is not going to suck you in, right? If you can land on a black dwarf. But if going back to Paint It Black, going back to the song, the lyrics being poetic now, maybe then I'll fade away and not have to face the facts. It's not easy facing up when your whole world is black, right? Painted black.